for the introduction. So, and thank you for being here for this for having the opportunity for having this talk. So the topic of the talk, as you can see here, is about Taylor bubbles, and actually we will speak about actually using Taylor bubbles or elongated bubbles in small channels can really improve or not mixing and mass transfer. Why we are studying this topic? While we are studying this topic, actually, this type of elongated bubbles are typical from a lot of application. You can see here, these are real in vivo. These are in vivo experiments. Should I stay here or there?
Probably there.
Okay,
yeah.
Sorry. I don't want to.
No, right.
Okay. These are in vivo experiments. These are real bubbles. Actually, we're injecting air inside the blood vessels, probably rabbit, in order to check air embolism and stuff. Or this is the classical example of ganglia in porous medium or in general microfluidics. There are also other applications where actually bubbles are studied in addition and in combination with heat or mass transfer. This is a case of bubbles of CO2, which slowly are getting.
Never touch the screen.
Okay, sorry. I'm a disaster today. These are bubbles that are of CO2, that are slowly dissolving inside the channel. Or these are experiments made in the group of Ilenia Battiato in Stanford. These are CO2 bubbles that form after a series of geochemical reactions. So the idea is to study how this bubble affects mass transfer in the surrounding liquids. This is actually the main idea of these studies. Or another type of application is typical of heat transfer community. So if you take a tube and you fill it with like a liquid, for example, water, you start heating up the channel, then the water start to boil, and you see that at one point you see the formation of these elongated bubbles, and then eventually other type of flow regimes like columnar flows. This is a big picture of the application that we are looking at. And before starting the technical part, I just want to start with this historical part. So usually people refer to this type of bubble as Taylor bubbles. For a while, I was speaking with a professor named Browner. I was trying to ask why people start to call this bubble the bubble of Taylor. So when we went back into the literature and find out actually the first two papers, to the best of our knowledge, but we have additional information, we are glad to complete this part. The first paper when they refer to Taylor bubble as Taylor bubble is this paper by Griffiths and Wallis in '61. And then in the Brown 65, they say, okay, from this point, we will refer to this type of elongated bullet-shaped bubble as Taylor bubble. They were probably our colleague in Cambridge. This is more or less what we reconstructed from the history, but still is not clear when in the community people start calling this type of bubble Taylor bubble. And later on, they also, probably this is because these works refer to works of Taylor, either in big channel or in small channel. And later on, when this type of bubble are in a very small diameter channel, they also referred as the Bretherton bubble, thanks to the famous paper. We will speak about it later on, the JFM of '61 by Bretherton. This is just a small historical part about the topic and why people call it Taylor bubble. What we want to do today, we just want to share some research we are doing in the context of elongated Bretherton or Taylor bubbles. So the idea is to understand, as you can see here, how the presence of this type of bubbles actually enhance or reduce mass transfer. So the idea is to consider different physical mechanisms like molecular diffusion, advection, and some superficial mass transfer mechanisms. So the idea is, if we have a bubble or a thin flow like this, does it help or does it not help in mixing and so on? This is actually the key question of the talk. Just to give a bit of context, I think everyone here is familiar with the classical Aris-Taylor dispersion problem, where we have like a classical pipe with a Poiseuille-like velocity profile, and if you inject like some concentration of a solute, it will spread accordingly to the classical Aris-Taylor dispersion. And the physical mechanism in a problem like this is just shear flow, which in this case is 1D, and you may have at the walls, let's say, superficial mass transfer mechanism. So basically, you can take or give some mass. Here, in the problem we want to study, is slightly more complicated, because then what we see here is the shape of the film region of the bubble. These are the streamlines. And actually, the flow, the shear flow is 2D, is not 1D. So we have actually the contribution to dispersion in both the axial direction. Then also the bubble shape is playing a role. So this is not a straight channel, but the film can change the shape. And then also here we may have superficial mass transfer. So in addition to the classical Aris-Taylor dispersion, we are actually accounting, let's say, with more physical mechanisms. This is the idea. And the structure of the talk is the following. So before going to into the details of dispersion part, I just want to briefly review the Brescia theory that allows us to describe the flow within the film of the Taylor bubbles, because I think this is necessary to better understand the mass transfer part, which is the core, will be the core of the presentation. So to start, actually, developing models to describe elongated bubbles is not easy, and we can do it only in specific cases and specific regimes. One of the famous models is the model developed by Brescia in '61. This model applies, so there's a lot of assumptions we have to make. So this model is, for example, it applies only if the geometry is planar or circular, and then we are restricting our analysis to systems where there is no gravity and there is no inertia. And then we also make other assumptions. See, the bubble is sufficiently long so that actually this is the typical shape. So we have like sort of spherical cap at the beginning, where actually surface tension dominates over viscous effects. Then you have a transition region. Then there is a region of the bubble where the film is flat. Then you see some oscillation, and then again, you see a spherical cap. This is a typical shape of the Brescia or Taylor bubbles in small diameter channels. And the theory I just want to review only apply in the central part of the bubble. So the theory is able to describe the bubble profile only in the transition region and in the uniform film region, but not in the spherical cap, because there you cannot use the lubrication approximation. And the main idea is the following. So you start from the problem. This is the problem in dimensional coordinate. So we just call small h the film thickness at the center of the bubble. We called L the length of this transition region between the uniform film and the spherical cap. We don't know yet how big is L. And R is the radius of the channel. The idea is to zoom on this transition region, and how we can do it to zoom, we just stretch the spatial coordinates in order to zoom in and to see what's happening there. So the idea is to define a scale parameter, which is called small epsilon, is the ratio between H and L, which should be small. We also require that not only H over L is small, but also that the film thickness is much smaller than the radius of the channel. So we know that H over R is smaller than H over L, which is smaller than 1. But still, we don't know the ratio between H over R. This will be verified a posteriori. This will be the result of the theory. One of the main results of this theory is to understand what is the scaling law between the film thickness and the channel of the radius. How we can stretch this coordinate? What Brescia did was to use the lubrication theory, which applies only when the slope of the interface is sufficiently small. You see that the axial coordinate over x is stretched in this way. So x is divided by h divided by epsilon, and the epsilon is small. So it's like the boundary layer theory when you stretch the axial coordinate, while in the y coordinate is just y divided by h, where h is the uniform film in the center of the bubble. And you can do this either in the front and in the rear of the bubble. This is the main main idea. We just are using the classical lubrication theory, how you can do it. So you can write down the momentum equation only in the liquid, because this theory actually, I forgot to say, neglects everything that's happening inside the bubble. So the bubble is considered viscid and with the zero viscosity. So we are actually solving only the liquid. So you take the momentum equation in the x and y direction in the liquid in dimensionless form, and this, you see that the problem is controlled only by two-dimensionless number, which is the Reynolds number and the capillary number. So the idea is, when we use the lubrication theory, is just to say, okay, if the product epsilon by Reynolds is small and also epsilon is small, the momentum balance in the x direction reduces to that one. So we only have pressure gradient equal to second derivative of the velocity, which is the classical way of the lubrication theory. And you see that the only way that these two terms, so the pressure gradient balances with the viscous part, is the only way to have the two of the same order is that epsilon should scale with the capillary number to the power of 1/3. So now, thanks to this simplification, we also have an idea of how small is epsilon. And if we do the same also on the boundary condition of the problem and blah, 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 you get that the pressure in this limit is just equal to the second derivative of the bubble shape, which is indeed the curvature. And so the pressure gradient is the third derivative of the profile of the field. This is the main idea of the theory. Then, given that, what you can do, you just can write a mass balance between, let's say, the transition region and the center of the bubbles in a frame that moves with the bubbles. You do some algebra, and then you define this variable xi in this way, and you find out that the film thickness of the bubble is described by this similarity equation, where eta is a dimensionless film height, xi is just the stretched x variable, which has inside this capillary number to the power of 1/3. It's nice because this is a similarity equation of the first kind. There are no any additional parameter. And if we are able to solve this equation, this is the main result that Bretherton obtained in 61, actually you get the bubble profile in all the central part of the bubble. How you can solve it? So the equation is that one. If you focus on the uniform film region, there eta is equal to 1. So things are not very interesting. All the derivatives are 0. It means that there you have no flow. This theory predicts only capillary-driven flows, but actually there is no flow in the central part of the bubble. While if you go a little bit on the right or on the left of this uniform film region, somewhere eta is slightly bigger or smaller than 1, there the bubble profile you can demonstrate is analytical, it follows an exponential. This is called exponential region. Or if you go a little bit farther, so when eta is much bigger than 1, then the bubble profile is parabolic. So this solution is analytical. And the fact that here the profile is parabolic is very important, because actually if you compute the second derivative of the parabolic velocity profile, so if you compute the curvature of the bubble profile there, and you can see here the bubble profile computed on the left and the curvature on the right, you see that when the profile is getting parabolical, the second derivative, so the curvature, is becoming constant. And this is the key part of the Bretherton theory in order to match what's happening in the film region with the spherical cap. Because since here we get that the solution is parabolical, the idea is, okay, we have a parabolical profile with a constant curvature. On the spherical cap, there is the cap is spherical, so the curvature is constant. You can just match the two. And by matching the two, we are sort of connecting, let's say, the spherical cap with the film region. And if you do the math and the matching here, I'm just reviewing the result, you get the expression for the h over r, which is equal to a number, which for the Bretherton case is 0.643, which multiplies the capillary number to the power of 2/3. This was the missing piece at the beginning. We just find it by the matching the spherical cap with the film region. And you see the Bretherton theory, these are results of numerical simulation that we did a few years ago. So if the capillary number is sufficiently small, as predicted by the Bretherton theory, actually this scaling law describes pretty well the experimental data. Then you see some deviation, but this is somehow expected. Okay, and this was just a brief review of the Brescia theory, and then you can do the same also in the back. And interestingly, in the back, you see that the profile has this strange and typical oscillation of the profile. Remember that if we increase the capillary number, this is a bit out of the topic of this talk, the shape of the bubble will change. So this idea that the spherical cap are indeed spherical is true only if the capillary number is small. But then if we increase the capillary number, maybe the front is still spherical, but then you see that in the back, you lose the symmetry between the back and the rear of the bubble. So then the procedure is slightly different. Okay, this is just a summary of the scaling one. So the idea was just to briefly review the Brescia theory. And now going back to the real topic of the talk is, okay, let's take the Brescia bubbles with all the assumptions that we made before, and try to understand how this bubble actually affects the transport of a scalar in the liquid. So the idea is that in the liquid now we can add an equation. This is a classical conservation law, advection-diffusion equation for the concentration. You see that the concentration is advected both in the U direction and in the V direction, so U and V. And both U and V, we can see it here, can be computed analytically based on the lubrication theory. So if we take the Brescia theory, we already have the velocity in the axial direction. We can also have in the transverse direction, just using the continuity equation. Everything can be done analytically. And this is the result of the velocity profile in the front and in the back. We can anticipate that in the back, every time you see these oscillations of the velocity profiles, actually what's happening is that here we see the sort of recirculation region due to the waviness of the interface. And this is just predicted by the lubrication theory on the Brescia problem. So the equations, again, is the classical advection-diffusion equation, where the velocity is given by the Brescia theory, and this is just the classical diffusion coefficient. We're considering diffusion both in the axial and transverse direction. About the boundary conditions, so both at the wall and at the interface, we were just assuming, assume that we have like a mass transfer mechanism of the first kind. Alternatively, it's like a reaction, first order reaction. In this case, you have that the flux is equal to K, a constant, which multiplies the concentration. So this is a classical boundary condition of the first kind. And you see that the flux is the normal flux. So for the wall, it's easy because the normal vector points downwards. But when the interface has a sort of slope, then you have to use the proper formulation of the normal versor for the problem. So this is the problem that we started with this analytical profile. And so the idea is, in order to apply the machinery, in order to obtain a model, we have to make the problem dimensionless. How we can make the problem dimensionless? We're just introducing here some length scales. So we are using the length scale, so the film thickness in the central part of the bubble to normalize the y direction. We are using the same L to normalize the x direction. It's the same one as we got with the Brescia problem. So we are using actually the same scale parameter for the flow and for the transport here. We just use the reference velocity, bubble velocity for bubble speed in order to make the velocity dimensionless. And this is the dimensionless equation. You see that there is only the classical dimensionless number that appears are the Péclet number, so the dimensionless number which balances advection and diffusion, and this scale parameter epsilon, which is the same as before. Actually, every time you see epsilon is the capillary number to the power of 1/3. And we already know that this is small because the Brescia theory applies only a small capillary number. And then once we are here, we can do the same also on the boundary conditions. So the dimensionless boundary conditions are here on the bottom. You see that actually the flux at the wall or at the interface is controlled by the Sherwood number. Also here in the literature, in some works, they call it Sherwood number. In other works, they call it Damköhler number. it's not clear to me which one of the two is the right choice, but actually probably is the same. It's just a matter of the community or whatever. So this is the physical problem. Then actually the only way to solve it is to solve it numerically in order to get the transport in the surrounding of the bubble. But we didn't want to go through the numerical part. So our idea was to try to obtain a reduced order model for the problem. So instead of focusing on the concentration field as a function of x, y, and t, what we wanted to do is, okay, why don't we try to obtain an equation for the average concentration, like xt, which is a function of xt. So like it's like a sort of average on the y direction. But the problem is that we cannot just average the result on the y direction. What we want to do is to really obtain a conservation laws for the average concentration. This is actually the same approach of the classical Aris-Taylor theory. And the way we can do it is, okay, we just take the dimensionless equation I was showing before. We just can expand the concentration in the power series of this parameter epsilon, like C0 plus epsilon C1 and so on. So we transform like the boundary value problem in a cascade of boundary value problem, and we can just solve them sequentially. And doing so, we will get an equation for the average concentration. Here, I'm skipping all the technical part. So if you are interested in the technical parts, how we were handling the equation, the boundary condition, and so on, feel free to ask us afterwards. I didn't want to put too much math inside, too much derivation inside the presentation. But the main idea of the derivation is that you just take the equation, you plug it in these expansions, you get an infinite series of equations, and you just solve them. But while you solve this equation, you want to guarantee that the solution is unique. And there are several ways to guarantee the solution is unique. In some of works like the Mauri 91, this is called solvability condition. In the work by Péclet, they recall it as Fredholm alternative, or there are also other strategies like in the work by Elena Battiato and 2010. But the main idea is that if you want to see the Taylor dispersion, you have to choose the proper time window and spatial window for the problem. So you cannot focus on length scale that are microscopic. In this case, microscopic, it means like the uniform film region, because then it's too small. You cannot focus on microscopic, on macroscopic length scale, like the big L, because then this is too big. The same applies for the time scales. So you cannot be at time scales which are too fast, like on the same order of the transverse diffusion, but you cannot even be on time scales that are too big, like on the axial diffusion. So in order to see the Taylor dispersion, you have actually to be on a length scale, which is actually the geometrical mean. I still don't know why, geometrical mean of the two length scale, and on a time scale, which is actually controlled by the Péclet number. This is the only time scale where all this machinery of the Taylor dispersion actually works. This was just a summary. Then, if you want to additional details, we can discuss it later. And given that this is the result of this machinery, this is the classical two-scale asymptotics or some kind of homogenization. Even if in this case it's not a real homogenization, where there is no like continuum and pore scale. The idea is that you get an equation, a conservation laws, Advection-Diffusion-Mass-Transfer equation for the average concentration. This is one-dimensional, and you can see different things. First of all these colored boxes highlight the different physical mechanism that appears in the equation. U star is the effective advection. Actually, averaging the problem, you obtain this U star is a sort of effective coefficient, which actually depends on the shape of the bubbles and so on. This star is the effective diffusion coefficient. You can already see that it has the same structure of the Aris-Taylor dispersion. This star is proportional to the square of the Péclet number. We'll be back to this point later. While the Sherwood number star is an effective source term, which appears in the equation, again, is proportional to C. through the boundary condition. So the starting equation, the mass transfer mechanism was imposed as a boundary condition. And while we averaging the problem, then we obtain that in terms of the average concentration, the flux at the walls or the interface is actually here in the equation as a linear term in the equation. These terms looks complicated, but at the end of the day, we can show that only the first term of the yellow box and the first term of the blue box are important. The other are just minor corrections. Once you get the equation, again, we can go back to the picture. So this is the same, again, approach of the Aris-Taylor dispersion, but now the effect of U star and the effect on U star, D star, and Sherwood star accounts for the flow in two dimensions, for the bubble shape, and also for this mass transfer mechanism. Now the idea is to try to go a little bit into this coefficient and try to understand a little bit more about the physical mechanism. Before doing that, while you are applying this machinery of the to-scale asymptotics, you also obtain a precise applicability map, which is telling you when the model is applicable and when the model is not applicable. The model is, again, is applicable only when the epsilon is small, so the scale parameter is small. Péclet number should be bounded 1 over epsilon square, and so on. And this is a graphical way of bounding the validity of the model. Interestingly, you can also identify different regimes. So if you're working on the box 1, you have like advection, effective advection, effective diffusion, and effective mass transfer. But then, if, for example, you reduce the Sherwood number, you go on box 2, you lose the effective mass transfer mechanism. You only have effective advection and effective diffusion. And you can play in this plot as you like, and you can obtain several regimes up to the point like on V, small Sherwood, a small Péclet, everything is dominated by diffusion, and you actually have no effect of advection at all. What about this coefficient? This star, it has the same structure of the Aris-Taylor coefficient. If you just rescale the Péclet number, instead of the Péclet number I was showing in the beginning, you just rescale it as the Péclet number of the film. And this is really the same scaling law as in the Aris-Taylor dispersion problem. The only difference is that here you have the effect of the bubble shape and the velocity is two-dimensional instead of one-dimensional. Concerning the U star here, it depends mostly on the bubble shape, and you can see it there. While the effective mass transfer, I think this is the most interesting part to me, you see that it scales as 1 over eta. Eta is a dimensionless bubble film thickness. What does it mean? When the bubble thickness is small, this coefficient is much more important. Then, when the eta is increasing, actually this Sherwood number is decreasing. What does it mean? And we expect that all the dynamics, the mass transfer dynamics, actually will happens inside the uniform field region. While on the front part of the bubble, we don't expect a strong impact of the mass transfer. Why is it so? Because actually here the film is confined in a very narrow space, and if the mass is taken from the boundaries, there is not a lot of availability of the solute here in the film. But here, actually, there's if you take like an infinitesimal part of the liquid, actually the solute is spread over a wider volume, so it's more difficult to take this solute. And now I want just to show some results. This is an equation that cannot be solved analytically because all this coefficient depends on eta, which is a function of x, so it cannot be solved analytically. We have to solve it numerically, but this can be done easily using, for example, MATLAB. And here we just wanted to show some result. This is a video of a case of high Péclet and high Sherwood number. And we call this example dirty pipe. It's like that the film is initially clean, so concentration is equal to 0, and is like approaching a pipe which is dirty with concentration 1. And here also the mass is taken from the boundary. As you can see, that as far as the front advances, then the color diminishes. It means that actually the the front is not even able to reach the uniform film region. This is only one example. Then you can do all the regime that you like. So then we try to summarize these different regimes on a map as a function of a Sherwood number. So here we have high mass transfer or zero mass transfer, Péclet. This is a case with high advection and high mass transfer. You see that actually the front is not even able to reach the uniform film region because the mass transfer is so high that everything got cleaned. Oh, I touched it. Sorry. Okay, thank you. Everything got all the mass is taken before reaching the film region. But then, if you decrease the Sherwood number, so if you decrease, you are killing the mass transfer mechanism. You see that you really approaching an advection-dominated case, where actually the front is really advancing and going inside the uniform film region. And you can do the same also reducing the Péclet number, so going to a regime where advection is less important, and you see probably everything is more sort of diffusion control. And then depending on the application you're looking at, you can sort of span all the parameter space and study the problem you're more interested in. Another case that we were trying is this case. So you can also observe strange effect. This is the formation of an hotspot. So here the idea is to start, let me stop the video. The idea is to start from a channel, from a film that is actually, let's say, dirty, so with concentration 1. And here there is a mass transfer mechanism on the wall, which is taking the solute. And if you choose your dimensionless number in a way that the Péclet number balances with the Sherwood number, what you see is the formation of an hotspot. You see that the uniform film got clean immediately. There the mass transfer is very fast. But here advection is really sort of, it's like pushing all the dirty part here, and then this is slowly disappearing. This is like when you are cleaning the floor and then the dust sort of accumulates. Why we see this hotspot? Just because there are different regions of the bubble, which the film is dominated by mass transfer, while the front is dominated by advection. So here is just pushing the solute in this direction. This is just one example of things that we can investigate with this type of analysis. And interestingly, in the back of the bubble, the situation is even more crazy. If you remember, at the back of the bubble, the bubble profile has this type of oscillation. It means that there the velocity also can change direction. So you see the formation of these recirculation vortices, and exactly at the point where you have the recirculation vortices, you see these local spikes or local minimum of the superficial mass transfer. So at the end, most of the interesting dynamics in terms of mass transfer appears in the uniform film and in the back, where we see these recirculation vortices, which actually enhances the mass transfer mechanism. And this is just a video of the solution for a case with high advection and not too high mass transfer, just to show that how the front propagates in the back of the bubble.
Excuse me, I didn't understand. What do you mean by mass transfer here? You're not talking about transfer into the bubble, right? Everything is outside the bubble.
Okay. With the mass transfer, I mean that the boundary conditions are like these two. So the concentration is actually taken from the wall in this way. So the flux is equal to a constant K that is proportional to the concentration at the wall or at the interface. This is the same like of having a chemical reaction of the first kind on the wall, but this is we call it passive. This is usually called passive scalar because actually the concentration is not affecting the velocity field. So the velocity field and the concentration field are decoupled, but the concentration can let's say, increase or decrease through to these two mechanisms at the walls. But then you can change the boundary condition and put the chemical reaction of the physical mechanism you like the most. And I didn't mention, but in the uniform film region, we didn't show the results about that. The nice thing is that the equation simplifies a lot because there eta is equal to 1. All the derivatives disappear. The equation reduces to something like this, and here the solution can be found analytically. So here we're not showing any analytical result except for the green function of this function. Based on the green function, which are shown here, you can really obtain all the analytical solution that you like in the uniform film film region. So to sum up, what we did was to try to understand if or whether the presence of the bubble enhances or reduces the mixing and mass transfer and transport in the liquid surrounding the bubble. This work is really focused only on the film region of the bubble. And this was a sort of generalization of the Aris-Taylor dispersion, the classical film flow, Landau-Lewis, Derjohn-Bretherton problem. And this is the main idea, and all the results are summarized in this publication. And what we are doing now, we are moving in different direction. One direction is actually done by Paolo, his PhD student. We are moving now more on the heat transfer problem. Ideally, we want to extend the heat transfer model to the Taylor bubbles, but we are not yet there. We are not there yet. We focused first on another flow regimes, which looks simpler, but is not. Paolo can confirm it took like a while. So we developed a similar model to describe the heat transfer in a corannular flow configuration in order to understand how the two phases, again, also here, can enhance or retard heat transfer. We're studying here the classical Greitz problem, where we impose heat flux at the walls, and we want to understand whether and how the heat is transferred from one phase to the other one. And here we're developing a model. Again, similar. The approach is similar to what I showed in this talk, but the mathematical part is slightly more complicated because here we have like two domains which are communicating and are through the interface, and this gives origin also to coupling terms like cross diffusion, cross advection, so that then the result is slightly more difficult to analyze. But Paolo is here, so if you're curious, feel free to ask Paolo about about these details. And with this, I want to thank you for the attention. I'm open to any questions. Thank you.
This epsilon you had, it's dependent on the Kepler number. And you have some requirements that this should be small. At the same time, you are in a regime where the Kepler number should not be too small, right? Because then you're going back to having just spherical caps on both sides. So how large is this region where you both have the epsilon small but not too small? I think that also relates back to several of your sort of older regimes. Are older regimes inside where this is fulfilled?
Okay, let's put in these terms. This is a good question in the sense that the Bretherton theory only applies when the capillary tends to 0. So this is the result of made with numerical simulations, like in a straight tubes. You see that the Bretherton theory applies up to capillary. This is the capillary based on the bubble speed and the fluid properties. -2, 10 to the -2. If you go beyond 10 -2, then the Bretherton theory, the way I present today, is not valid anymore. So all this analysis of the transport actually holds only if the capillary, I would say, is smaller than 10 to the power of -2. But then it should be also bigger than, let's say, it should be sufficiently big that you can neglect like disjoining pressures or other molecular effects. So there is a range of validity of the theory. I would say no, -6, -2, to give a sort of broad range of the. And then another things connected to this, because you see that if you increase the capillary number, then you lose the symmetry of the bubble and things changes. And then it's very difficult to apply the lubrication theory when the capillary number is finite. And then concerning the transport problem, this is what Paolo is doing. Actually, in his work about heat transfer, he's doing the expansion for the heat problem, not using epsilon, but using correct epsilon multiplied by the Péclet number. In this way, this is more accurate, maybe more wide for the transport problem.
Thank you.
But the real answer is that this is the only regime where we can use lubrication theory. Otherwise,
there's a question on.
Yes, there's a question on chat. So can you read it loud? Since your model extends Aris-Taylor dispersion to include surface mass transfer with Taylor bubbles, could you share a bit about how sensitive the effective Sherwood number is to the bubble shape oscillations, especially at the rear meniscus?
Okay. Let me take the expression first. So the effective Sherwood number, you see here the full expression. Actually, you see that here, this is proportional to epsilon square, so this is somehow small, the second part. The third part is a function of the derivative of the bubble profile. So then when you are far from the uniform film, this derivative may be important. But most is controlled by this 1/eta part. And if we go to the last plot in the rear of the bubble, when we have this oscillation, this is the plot of the effective Sherwood number. So Sherwood number is 1/eta. And since here eta oscillates around, so it can be bigger than 1 or smaller than 1, this is what is giving you this oscillation here in the back. And when the profile is minimum, the effective Sherwood number is maximum. And I don't remember the exact number, but there is a minimum. So if you take the Brescia solution, the minimal thickness is probably 8.7 or 8.2. Now I don't remember the exact number, but here at the minimum, so the effective mass transfer is the maximum. And it probably is here like the center of this vortex here. And probably the way we try to explain is that here, due to this recirculation region, it's like you have a lot of availability of solute, which is just stay there. This is why when you average the problem, you see a spike. This is a Sherwood number for the average concentration. So actually all these are effective mechanism. I don't know if I answered the question.
So as he posed a follow-up question also with the sensitivity. If it could be useful when trying to optimize mass transfer in porous media structures. Get larger structures.
Yeah, it could be. That could be a good idea. We actually haven't thought to go in that direction, but this can be a good, I think a very good suggestion. Maybe shaping the profile in such a way that you may enhance this. But here the trick, remember that the fluid-fluid interface is like a free surface flows. It's like a free surface. So the wall is no slip, but I think I forgot to say, but the fluid-fluid interface in this model is like a free surface. This is why you see these recirculations. If the interface would have been a no slip, then I think the result would have been different. But yes, this can be a good suggestion to try to optimize it in order to. I don't know how to do it, but how you can shape a film. But that could be a good suggestion. Thank you.
No, go first.
About the velocity here, the driving force of the movement is the inlet velocity. If you change it to the, for example, to the buoyancy force, then how these equations, these conclusions would change.
Okay, this is another good question. Let me just go at the beginning. In the film, so in the central part, driving force is only the capillarity, because the pressure gradient, when you use the lubrication theory, so if the pressure is the second derivative, pressure gradient is the third derivative, so it's only capillarity. But if you look at the whole bubble, then the fluid is pushed by the sort of Poiseuille velocity profile. If you add the buoyancy, it's more complicated. There is a part on the Breckerton problem where if you add the gravity, the problem is that due to gravity, you lose the sphericity of the cap, and then it's more difficult to make the matching between the spherical cap and the film region.
Because I have seen some studies on this. For example, they compare them numerical with the experimental, and they use the buoyancy to get this U large.
Yeah, in this case, you scale everything with the bond number instead of capillary number.
But are you talking about the same? Because you're talking about the buoyancy as the driving force for the whole bubble, right?
Yeah.
Not buoyancy when you also have
Flow.
For example, you can see the both of the ends of the column, and then the liquid is stable, just cover moves to the.
I think there are studies in that direction. Probably we haven't looked yet at that, but if you are curious, I can send you some reference about work where they were studying Taylor bubbles with flow and gravity. Things are a bit different because then
There's a small comment. You call those recirculation zones below the bubble there, but you actually have a transfer of fluid from the front to the back of this drop, don't you? So the drop is actually going faster than the surrounding fluids.
yeah, the bubble is always faster than the fluid. Because this is a result from the numerical simulation. You see the streamlines. So you also have recirculation inside the bubble. But in the model I showed, we didn't account for the flow inside the bubble, but only in the film.
Yeah, but is it then only recirculation in this thin layer, or is it actually then also fluid flow?
I think this is in the absolute frame. I think I have to check. I think it's local. It's local. Because then when you approach the uniform film, there's no flow at all. So it's like there is, the velocity here is decreasing, going to zero, then it's positive, negative, and then becoming positive again. Because using this lubrication theory, every time that the film thickness is below 1, it gives a negative flux. Every time it's bigger than 1 in dimensionless form, it's giving a positive flux. This is why you see this.
Yeah, so you actually have a negative flux along this thin layer.
Yeah.
We have a question here. Do you hear us?
Yeah.
Yes.
Okay, good. Hi, Davide. I was thinking we discussed a little bit some months before, because Federico and I are doing these experiments here in Oslo where we have this train of bubbles in a single capillary tube. And for some regimes and for some types of fluids, we were thinking that perhaps this could be Breckerton bubbles. We could have like films between the bubble and the tube. And then also with Alex, we were discussing, because the idea is like to try to get how the pressure drop on the whole tube relates to the flux, so the capillary number. And I remember that for a single bubble, you had like this relationship of a capillary number to 2/3, right?
Mm-hmm.
So this is the pressure, just so you're sure, it's the pressure outside of the bubble, right? It's the surrounding fluid. Correct?
Yes.
Yeah. So then the question is, we're wondering what happens if you have like a train of those bubbles, and if they are not too far apart. Do you see any hopes to extend this relationship to several bubbles?
Yeah, I think you should ask Paul about this. He's trying to struggle with this problem, and probably we can. So now we don't have the time now, but we can discuss it about. So I think this is part of what Paul was trying to do here with Alex, and it's difficult to summarize his model in 1 minute, but he can do it better than me. So maybe we can chat afterwards about it.
Okay. Yeah, sure. Yeah, we started talking some time back, but then I also stopped the experiments here. But we plan to continue these experiments soon. So it would be nice to have a little chat to see if we can correlate with the theory.
Yeah.
Good. Super. Thanks.
Welcome.
Any more questions?
Yeah. Other questions or comments or whatever?
Any more questions from the people on Zoom? Not?
No.
I think we can thank the speaker one more time.